Page 96, summative assessment number 1. It was number 1, eh? It says a hollow shaft transmits that power. We are having a hollow shaft. A hollow shaft. There is my hollow shaft. They say this shaft is capable of transmitting 300 kilowatts. And what is this 300 kilowatts? It's a power at 500 rev per minute. And what is this one? Sorry? Revolutionary speed. Ne? They say the maximum torque exceeds the mean torque by 15%. Therefore, our overload is equals to 15%, whereby we need to substitute 1.5. No, 1.15, including the full load. .15. So, must you understand this one? The first one is for a full load, then this one is the percentage. So after that, they say the shaft support a pulley placed 1 meter from the left hand bearing. But before that, they say the shaft is 2.5 meters long. So this shaft is 2.5. From here, from this end up until to this end is 2.5. And they say it supports a pulley. The pulley which is placed 1 meter from the left bearing. We are also having the bearing. So I'm going to draw a schematic drawing. The schematic drawing, it will be this one. The left bearing will draw it as a reaction there, the right bearing, and the left bearing as another reaction there, according to the statement. Again, they say the statement says the bearing are on the end of the shaft, right? Yes. So this is a schematic drawing. Therefore, from there till there is 2.5. And they say we are having a pulley here. The pulley, which is 1 meters long. Ne? Yes. So here, this arrow, this one here, is for the mass of the pulley. We know that the mass is always going downwards, right? So 2 tons is equals to what? In newtons. 2,000 newtons. Huh?
2,000 kilograms.
Sorry? 90. 19 newtons. 19,620 newtons. 2 ton. 2 ton. How many newtons? 2,000. How did you get to 2,000? Sorry? 19,620. You agree with this one? But let us understand this point. I want to get to 2,000. How did you find 2,000? It's 2,000 times 1,000. And what do we get? We get 2,000 what? So when do you get kilograms? When do you get to the kilograms? How do you convert time to kilograms? Yokushayile ne? Hayi kuhle. Kuhle mawubonile ukuthi ushayile. Okay. So now we have these newtons, ne? So they say this pulley, we know that the pulley it drives the belts, ne? So they say there's a machine which is located underneath the shaft, meaning if there's a pulley here, underneath here there's a machine which is being driven by this pulley. So there's a belt there. So this belt is pulling the shaft downwards with T1 plus T2, right? So the same way, at the same position, the very same pulley, it has another force, which is 3000 newtons plus 800 newtons. Again, this one is T1 plus T2 because both of them they are pulling the shaft downwards. Guys, you need to understand this one. This is not effective tension. It's not effective tension. So here, this one we can say maybe, okay, let me draw in this man. You are having a pulley somewhere there. There you are having a pulley. Then you put a belt. This belt it goes down. Or let me draw in this man. You are having this one here is the shaft. And you have another one here, this another shaft. This is the shaft, this one here is the shaft for the machine which is underneath the shaft. So in this case, you are connecting these two by the belt, right? If you tension too much of this belt, if there is a too much tension, therefore this belt it will pull this one downwards and it will also pull this side downwards. This side of the belt, when we check this one, it will pull this upward, it will also pull this upward. Just for instance, if you can come and hold here, and you hold here, then you squeeze these two together. When you squeeze these two together, it will pull this pull downwards, right? So that force which is pulling it downwards is the one on this side and the one at this side. Unfortunately, in this case, it pulls while running. So when it pulls while running, the tension, it won't be the same this side and this side as when it's stationary. When it's stationary, the tension this side and this side, it will be the same. But now because it pulls this shaft while running, therefore this side it will be T1 and this side it will be T2. So both T1 and T2, you add them together. Remember your effective tension, it will be T1 minus T2. Ne? So now the force which we are talking about, the one that is capable of pulling locosa down, capable of pulling the shaft down, that tension it will be T1 plus T2, right? So remember, even from the pulley we can able to calculate power. So when you are required to calculate, maybe let's take torque from the pulley. If this is a torque, your torque it will be T1 minus T2 times R. But if we are looking for the force that caused the shaft to bend, we need to add the two. I'm not so sure if this makes any sense. Just point with which part you this one. This one is when you calculate a torque. Remember, torque is equal to effective tension times radius. And how do you calculate effective tension? Effective tension is it not T1 minus T2? So the problem is we are all using T. We are using T for the tension, right? Well, no, for the torque. I'm saying this one's for the torque, right? We are also using T for the tension. So that is what makes maybe confusion. So in terms of us calculating the force that is pulling downwards, this is a tension. that is pulling the force downwards. Therefore, is T1 minus plus T2. So if we calculate the torque, when we calculate the torque, it must be effective tension times radius, whereby the effective tension you subtract. So now we are done with that part. So it means now we understand why here we have this torque, this force, and this force, right? Yes. So from there, let us calculate reactions. The reason we calculate reaction is for us to be able to find bending moment. Remember, this chapter is all about maximum bending moment as well as a maximum torque. So we need to find the maximum torque and find maximum bending moment. Then we combine these two. It will give us equivalent bending moment as well as equivalent torque. You get that part, ne? So for us to find a maximum torque, we need to focus on the twisting part. The twisting part is when the shaft is rotating. You get that part, ne? The twisting part is when the shaft is rotating. And when the shaft is rotating, we are given this information. Therefore, we can able to calculate maximum torque. Bending moment. With the bending moment, we must focus on the loading on the shaft. Then we'll be able to calculate what? Maximum bending moment. So, okay. Let us check. Which one should we start with? Maximum bending moment or maximum torque? Maximum bending moment. So maximum bending moment, remember, the moment you have a point load, only one point load. When I'm saying one, I'm saying at one point. For instance, here we have 1, 2, 3 forces, but they are found at this point. So if we have the point here with a point load, this one here is where we're going to find our maximum bending moment. I hope you will still remember your N4 syllabus. So now let us calculate the reaction. Remember, there's no need to calculate both reaction because our aim is not to find reactions, to find bending moment. So this one will be reaction at A, this will be reaction at B. So let us calculate reaction at A. We can also calculate reaction at B depending on which one do you want to calculate. Yes. So calculating reaction at A will take moment about B. So in this case, clockwise moment will be the same as anti-clockwise moment. Sum of clockwise moment is equal to sum of anti-clockwise moment. So what are the clockwise moment when we take moment about B? Sorry? Is reaction at A times 2.5. Do I have any other? No. Anti-clockwise? Sorry? Can you add? Again, they are acting on one point. 23,420. Yeah, ne? Then times 1 comma 1 comma. Agree from here to here is 2.5. What taking moment at B? Agree. So from here to here is 2.5. From there to here is 1. What about from there to there? 1.5. Self-Milan. Are you born this 1.5?
The 23,000. Can you add the 19,620?
This one, yes.
Yes. It's going anti-clockwise, right?
Yes.
Times the small distance here, 1, it's not 1.5.
Let us check. We are taking moment about B, ne? So when you take moment about B, then A, it will go and...
Oh, about B, I thought you took moment about A.
It's fine, eh? So what will be the answer for reaction at A? 48,000? 14,052. Iphelela 14. Wena le number wayibiza kanjalo. Yeah. 14052 Newton meter. Now we have reaction at A. There's no need to calculate reaction at B, right? So this reaction at the A is 14,5, sorry, what am I writing now? 14,052 Newton at A, right?
Yes.
So I can take this out. You know how to calculate. So now we're going to calculate maximum bending moment. And we have agreed that maximum bending moment, we'll find it at this point, right? So what will be the maximum bending moment? 14 times 1. Do you understand how to calculate bending moment? Zulu? You don't? Usabon? And if we are calculating bending moment at this point here, if we are calculating bending moment at this point, it's either you calculate from the right or you calculate from the left. Ne? So when you calculate bending moment, you take all the forces that are going up, you add them. But you don't just add them, you multiply with the distance. The distance from where you are calculating your bending moment. All that are going down, you subtract. For instance, when we are here at this point, when we calculate from the right, we have A. In which direction does A goes? It's up, ne? So if it goes up, it's going to be positive. You get that part, ne? So we need to multiply how long from where there is this 14,052 up until where we are calculating bending moment. How long is that? It's 1. That is why we have multiplied by 1. Do we have any other force? Which is that force? Sorry? This one? Yes, you're right. We also have this force here. You are right. We are also having this force here. Ne? So, and we are taking bending moment here, right? So it will be this force which you said it was 20 something, ne? So it will be, and this force is going down, right? It will be minus what? What was that force? 23,420, ne? Multiply by how long from here up until to here? From where we are calculating bending moment at this point here. So how long from this point here up until where there's this force here? It was 0, ne? So we are going to multiply it by 0. So what do we get? We get 14,052 Newton meter. So this one is our maximum bending moment on this beam. Yes. Remember I said to you when I started, I said you can choose to calculate from the left or you calculate from the right. So the moment you choose the left, currently we are calculating bending moment at this point, right? So when we calculate bending moment at this point, you need to choose one side. It's either you choose the side of where you are calculating bending, the right side of where you are calculating bending moment, or the left side. If we calculate from B, the same answer will come out, the same, exactly the same. Yes, so if we are checking the right side, it means is this force here multiplied by this distance there. The same answer will come. You understand it? Okay. So we have this as our answer. Then Let us calculate the again, we said we need to calculate the two. What do you call this one? We need to calculate the maximum bending moment and maximum torque, right? So how do you find maximum torque? Sorry? What is it that we should calculate? We must first calculate T mean, and we find T mean from the power formula. This is our T mean, all over 60. So it means T mean is equals to 30 P over pi n, which it will be 30 multiplied by 300 exponent 3 all over pi times 500. And what do you get as your torque? Sorry? No, the substitute. You can substitute the way you understand. Guys, I thought maybe I'm teaching the N6. We are doing mathematics N6. How many times have you manipulated the T? Yeah? You understand? Or I was supposed to say 60 over 30, or 60 over 2. Guys. But anyway, if you understand it that manner, do that one. What which you understand? 5, 7, 2, 9, 5, 7, 8. This one is our what? T mean. If you check our maximum bending moment and torque, they have the same SI unit, ne? Yes, so meaning we can able to combine them easily at the end. Our T max is equals to what? Overload times T mean, ne? Times T mean, which we have 1.15 times 5729. And what do we get? 6589, comma 015. Ne? Yes. Come again? Yes, do not forget this one. It must tell that you are engineers in making. One day the companies they're going to rely on you. Serious, one day the companies are going to rely on you. Question number 1, they want us to calculate the diameter of the shaft. Ne? The diameter, remember this is a hollow shaft. Ne? Yes. So in this case, from N5, you know that T max is equals to pi over 16 times shear stress times d to the power 4 minus d to the power 4 all over t. Ne? So in this case, the formula is still the same. The only difference is now, because we are considering both bending and twisting. Ne? For N5, we were only considering twisting. You were not considering bending. So this time around, this one is you are no longer going to substitute T max. You are going to substitute T equivalent. Ne? Yeah, equivalent torque instead of T max. So the question is, how do we calculate equivalent torque? Sorry? We don't directly add the two. Ne? So, look here. If you go to page 83, Page 83, you will find that torque equivalent. You will find that torque equivalent is equals to bending moment square plus T square. So therefore, you will be able to substitute this one there. You get that part, ne? So, if you also go to page, which page is this one? Page 86. On page 86, you will find that you have ME is equals to this one into D to the power 4 minus D to the power 4 times shear stress all over 32 times D. So now, we are having this formula. Let me write them both down here. The second one is this one. Yeah. The other formula, it will be TE is equals to pi over 16 times shear stress times D to the power 4 minus D to the power 4 all over D times shear stress. So as you can check, we have equivalent bending moment, and we also have equivalent what? Equivalent torque. So how do you find equivalent bending moment? You find equivalent bending moment as your equivalent bending moment. It will be 1 over 2 into this one plus TE. Meaning where there's TE, you can just substitute this one. You see that part? Ne? Yes. So it's either you use one of the two formulas to calculate diameter. Unlike on ON5. ON5 you were only required to use a torque. So this time it's also supposed to use what? Bending moment. So the question is, we have this diameter and this diameter, and it's for the same shaft. So which of the two am I supposed to use? Yeah? Which of the two am I supposed to use? The small one. How do I know which one is the small one? I have this diameter and this diameter. I'm asking which formulas will I use? Should I use the ME or should I use the TE to calculate diameters? The what? The ME. Why ME? There are two things here. If you check here, let us start with the one which is talking about. Let us check here. We are given this stress, right? And we are also given this stress, right? If you check, when you load a shaft, what's going to happen? It's gonna bend, ne? As it bends, meaning there will be a bending stress there. You get that part, ne? So if you have only a bending stress, you will calculate using this one. So if ever now you start twisting the shaft, when the shaft starts rotating, if it fails, it will shear, right? So when it shear, if you are given a shear stress, you will use this formula. Why two? Oh, it is one. It's only one. Thanks. Let me take off this one. Oh, you also cop your to share stress. Okay. Yeah. So sorry about that, guys. It's supposed to only to be one shear stress, ne? Yes. So if you are given the bending stress, you will use a bending moment, ne? If you are given a shear stress, you use what? Torque equivalent. We will use the second formula. The challenge comes. What about if you are given two of them? Or what about if you are given two of them? In this case, they want you to test which one are you going to use. So you'll use both of them. Meaning you'll calculate diameter from this formula, you calculate these two diameters from this one, you come and calculate these diameters from this one. Then you conclude at the end which one you are going to take. Also,
how will you know which one to take?
You must take the one that can accommodate both.
The allowable.
Yeah, the allowable. You know, this term was from previous subject. Okay, let us for instance, you have, let's take we were having a solid shaft, ne? This is a solid shaft. So with the solid shaft, you calculate. As you calculate, then you find that it has the diameter of 82. Then this one is from when you were using the equivalent torque. When you use equivalent bending moment, you get 92. When you use equivalent bending moment. So which one are you going to use as your diameter? You're going to use 92 as your diameter, ne? Yes. So it means you need to calculate and check which one you're gonna use. You get that part, ne? Yes. So after you have, let's take for instance, you have calculated, ne, and get 92. It means you need to take this 92 and substitute back and calculate your stress, the new stress. You get that part, ne?
Yes.
Yes. Yeah. Do you get that part, guys?
Wait, sir, can you repeat? You said you can have equivalent diameter and diameter.
This one, I'm saying when you calculate this diameter from equivalent bending moment and you calculated this one from equivalent torque. So now you are having these two diameters because you were given both stresses. So bending stress. So which one are you going to use? So they said they will choose this one, the bigger one, because the bigger one, it can also accommodate the smaller one. For instance, if we check, we will take 82. If we take the bending moment, the diameter of the 82, it means this one, it won't sustain a bending stress. It will bend quicker because in this scenario, it needs a minimum of 92 for it not to bend. But if we choose 92, this one it won't shear because in order for it to shear, it needs the minimum of the maximum of 82. For it to shear, this one from here we're having a shear stress. For this to shear, it needs 82. So if we come with 92, it means now we are 10 units more. Therefore, we are safe. That is why I was talking about allowable. Yes.
So this question you use ME.
No, this I was just giving example. I don't remember I was asking which formula are you supposed to use between the two. And then he said in this case we're supposed to use the equivalent bending moment. Then I said yes, because we are only given equivalent bending moment. Then I said on some other scenario you will be given the two stresses. So if we are given the two stresses, therefore, you need to calculate diameters based on the two formulas. Then after that, you choose your diameter. Which diameter are you going to choose? How do you choose? You choose the bigger one. Why do you choose the bigger one? Because the bigger one can accommodate the two stresses. Then after choosing your diameter, you recalculate your stresses. Agree, you still having bending this one. Yes, then you have the new diameter. It will be having the new diameters. Therefore, you calculate the new stress. If you are going to take from the bending stress, when you calculate this one, it will come back the same as given. But this one, it will change because when you calculate the diameter here, we got 82. You get that part? Me? Yes. So in the case of this one, choosing the smaller diameter, or the bigger diameter from the smaller one. This one you do it when you have a what? When you have a solid shaft. In the case of hollow shaft, it's not easy to choose checking on the diameters. You must calculate the area of the shaft. Again, now you'll be having capital letter D and small letter d. Yes, from this one you will be having this one from what? From the bending of the stress. You calculate again the D and this D. Then you have another diameters from the what? The shearing of the beam. So in this case, it's not easy to choose from diameters because you may find that this diameter is bigger than this one. But this one, you find that is smaller than this one. It becomes difficult. So in this case, you need to calculate the area. So the area is the one that will tell you which one you should choose, which diameters you should choose. But if it's only if it's only a solid shaft, you choose based on the diameters. Because if it's a solid shaft, if you calculate the area from the smaller from smaller diameter, you will get a smaller value of area. Hey guys, can I take a question this side? A question, yes?
What is tensile diameter and then substitute negative to
Stress.
say, let's say it's effective bending moment, say.
Yeah.
So
Yeah.
my substitute effective torque
Pen.
with the
The new stress, yeah. So that other one you just copy it as it is. But you only do that one. You only do that one. Hey guys, wait a bit. Guys, wait a bit. They did not complain when I said last week. I said you didn't come on Friday. So why do you cry for 10 minutes? Can you see? Just like number 2, 1.2. In this case, they are telling you to take the diameter which you got and substitute on the other formula so that they can get your shear stress. You get that part, ne? Yes. So guys, tomorrow we will look on the cantilever. Cantilever is whereby, for instance, let's take you are having a pulley. Not a pulley. Let us not go far. You are having a wheel. This wheel is attached to the car. Can you see this one here is a car? Can you see here you have a force. So this wheel, it acts as what? This shaft here, it acts as what? As a cantilever. So we'll talk about that tomorrow. Then after that, on Thursday, we'll check how to calculate bending moment when we have both vertical and horizontal forces. Yes, we have scenario whereby we have both of them, meaning we need to find a vertical force, a vertical bending moment, and horizontal bending moment. In that case, we end up calculating maximum resulting bending moment.